Okay, so we're going to continue on with some organics. We're going to talk about some properties of organic compounds today. One of the last things I wanted to talk about before I move on to that, today I'm using a red pen, is polymers. And I mentioned them a little bit when we talked about PVC. PVC, so a polymer is produced when small molecules called monomers, so that's the vinyl chloride is the monomer, is bonded together to form to form larger and larger molecules. So you take the subunit here and you stick them all together in order to form this. Examples of this are the polyvinyl chloride and vinyl chloride. I think I spelled vinyl around there. Vinyl chloride, so PVC. Cellulose is another example of it. Cellulose, which is used in plants as their cell material. Here, I'll give you guys one. PE. What is PE? When you look at plastic, okay? Well, that's polyethylene. So what do you think the main unit is? Ethylene. What is ethylene? Do you guys remember ethylene? C-double-bond-C? Yep, that's all it is. So polyethylene plastic. So this is out for Alyssa and to Cheyenne, who are going to be talking about plastics a lot. This is what polyethylene is. So when you look at these things, you know, if there's polypropylene, so there's polypropylene. Well, what's propylene? C-double-bond-C, CH3, H. There's your propylene. So there's 3 of them into there. There's the double bond. So that's when you say something is polypropylene. Yeah. How about polystyrene? Because you guys have probably heard of polystyrene. I want to make sure I spell it right. Styrene. C-double-bond-C with a benzene ring there. These are the functional groups. And then you just connect all these together. So when you connect them all together, you just get like something like this. So you got your, C, here's your H, here's your H, here's your H, here's your Cl, and then this is connected to another one, Cl, and just keeps going and going and going. And so you get your unit right here, and then it just keeps repeating itself. So that's what polymers are. So when we talk about plastics, and we talk about them, we're going to be talking about them migrating in the environment, because that's what happens. Where right now I'm really into microplastics, nanoplastics, and how they transport in the environment. When they break down, we're breaking them down into smaller and smaller of these units. And we're going to talk about biodegradation, we're going to talk about remediation of these things. But you can see and so we'll come back to this idea is, how are these broken down? Why are they not broken down in the environment? When ethylene is very easily to break down. These things as monomers are very easy. It's once they get all stuck together, it's really hard for microorganisms to get in here and to eat this. It's really hard to break these bonds. And so they become very, very stable. And this is why, you know, cellulose is you know what cellulose is. It's in, you know, trees and stuff. It's really hard to break down. It's because it's very hard to break down, and that's what they use it for. So it's a very important thing. So I just wanted to make sure we brought up polymers right now. Okay, so now what we're going to do is some physical and structural properties of organic molecules, because this will come into play when we're going to be talking about their fate and transport in the environment, because that's what our ultimate job in this class is to talk about the fate and transport of contaminants. And so we have to understand some of the basics of how these contaminants move. So one of the big ones, so we're going to be talking about, let's see if I can write, structure and physical properties of organics. Okay, so one of the first ones we're going to talk about is dipole forces. So we already talked about this. This is the idea of a compound being polar versus non-polar. So we've already kind of talked about this a little bit. The bond movement with covalent bonds, we have a positive and a negative end. so there's attractions to them. So I abbreviate just so you guys know. If you see this is positive, and this is negative. The reason I write the VE after the end of it is because if you just put a plus or a negative, you won't know if that's like just a dash or what that is. But if I put the VE after it, it means positive or negative, just so you guys know that. So this is positive and negative forces that are attracted to the ends of between two molecules. Okay, so it causes attraction. So what's the big thing about that? Well, when we increase attraction, and if you don't remember what polar and nonpolar is, go look those up in a basic chem book. When we increase attraction, we decrease the vapor pressure, and then we increase the boiling point. Okay, so when we say we decrease the vapor pressure, it takes more energy to vaporize it. Okay, so if we're talking about like volatile organic compounds or volatile organic carbon, VOCs, when we have a polar molecule and there's more attraction to each other because there's a positive and a negative end and we're polar compounds, it'll decrease how much it is VOC. Okay, so it won't volatilize because it decreases the vapor pressure, it increases the boiling point of the compound, makes it a lot more stable. So as we see those things, we're going to see more attraction. And one of the things that we'll talk more about too is that most clay, a lot of things under normal pHs that we find in the environment, especially clay, are negatively charged. And so anything with a positive charge is going to stick to them. And so we get a lot of clays with a lot of things that zorb onto it. Remember zorb? We're going to see a lot of zorption occurring. So we're going to be talking about these. So dipole-dipole moment, very important, knowing if it's got a polar or a nonpolar end. Okay? Well, this is one important part of attraction between things. There's also London forces. London forces. And this is what's called a temporary dipole. That's when the electrons move to one side of a nonpolar molecule. Okay, so you can get these temporary dipole where instead of just being a definitely polar molecule versus nonpolar molecule, you can get these temporary dipoles. This will induce a dipole in the very nearby environment. And so these are called London forces, and they're very short-lived. So it really depends on the shape of the molecule. So the more electrons from the nucleus, it's easier to do this. So an example of this, just to give you guys an example of a temporary dipole that's very important for us, is when we get to the halogens. So we get fluoro is less than chloro, which is less than bromo, which is less than iodo. So an example here is the boiling point, BP. Again, I've used it up here before too. The boiling point of, say, bromoethane versus the boiling point of chloroethane. Okay, so the boiling point here is 38.4 degrees C. Here it's 12.3 degrees C. Okay, so this takes a lot more energy in order to make it go into the vapor phase. There's more attraction when you get to, so you have this higher boiling points and stuff like that. There's more attraction of the molecule because it's greater to form these temporary dipoles. So when hydrogen is involved, this is called hydrogen bonding. So you should remember H bonding. It becomes important when there's hydrogens involved. And so we can see things like, let's look at an example here of ethanol versus dimethyl ether. So ethanol is CH3, CH2OH, while dimethyl ether is, here's one of my methyls, here's my other methyl, and then an ether group has got the oxygen in the middle. Okay, so this one has a boiling point of 78.5, and this one is negative 24 degrees C. Okay, so when there's hydrogens involved, like here, this little hydrogen right here, you're going to get hydrogen bonding. And when you get hydrogen bonding, it totally changes the boiling point, which changes how much attraction there is. So when you increase the boiling point, you increase the attraction. You also decrease its vapor pressure. So this will go to a gas very, very quickly. This one takes a little bit longer to get into a gas phase into there because of that hydrogen that is sticking on the end. So when we look at different molecules, again, if the oxygen is in the center, no hydrogen bonding. When we look at the chloro groups, the fluoro groups, and the temporary dipole is another big area of it. Okay. Another thing that affects the forces on it is the size of the molecule. So the size of the molecule here is the larger it is, it'll have increased boiling point. So like we look at pentane versus hexane. So 5 versus 6. Pentane is 36 degrees C versus hexane is 69 degrees C. So, okay, so that's another thing. And also the surface area increases it. So if we have the surface area, I'll just write this here, surface area. If we have more of a linear molecule, so it takes up more surface, it'll increase the boiling point too. So a lot of these things impact but the big thing for us is, how does it get into a vapor phase? Why is this important? Well, one of the reasons that vapor phase is really important is, I mentioned with VOCs, but like getting into somebody's basement. So vapor extraction is a really big thing. So I was dealing with a site where we were looking at TCE spill. It was up in Rockford, and what would happen is the guys would pick up the waste solvents from like Hamilton Sunstrand up there. And they were supposed to dispose of them in a proper way. But what they would do is they would drive around to this really sandy pit, this like right near the railroad track and down this back road. They would open their valves and they would just dump it. It was their area to dump. And so there's a whole bunch of these spots all over, especially the south side of Rockford. And so they would just dump them into these sandy areas. It would disappear because, it would just go away. It would also volatilize, but they would get rid of like TCE into their basements. Well, then what would happen is then homes built up around these things. And so one of the sites I was dealing with, there was a playground right above it where they would dump. But the homes in the area, they would get vapor into their basements. So these things would become volatilized, and they would become a vapor, and then they would move up into people's basements. And then people in their basements, as we talk about TCE more, because of that carbon-chloro bond, you got to keep that carbon. When we got these halogens mixed in, causes problems. And so it was getting into people's basements. And so vapor extraction, looking at vapors in basements is a big thing that can come from a spill that is in contamination. So knowing about them. Also, so that's one side of it, why this is important. Another side of it, I got to remember, and clays. I talked about clays and it's sticking to things. So understanding the geology is really important because if we understand the physical properties where it's going to be stuck to it, we're going to see this attraction occurring. When we have absorption occurring and we understand the geology of the sites, and then we look at the soil properties, we look at the geologic properties, we'll talk about this more. We're going to talk about KOW, KOW and KOC here, probably either Wednesday or Monday. We're going to be talking about these properties of soils. We're going to look at the octanol water partitioning coefficients and the amount that goes into organic carbon. And then knowing these principles and knowing the amount in your soil will tell you how much of it is going to absorb onto your soil and how much of it can move and migrate, because we're looking at bait and transport. The third part, why this is important, is dealing with remediation of a site. So when sites get remediated, what we can do is understanding how something absorbs onto our clay particles. So when we know the KOC and the KOW, well, how could we get past the absorption? Well, what we can do is increase the boiling point or go past the boiling point of a compound. So understanding what the boiling point is and how those attractions work, then we can get it to go into a gas phase. So we can use it as a cleanup strategy. What they'll do is it's called vapor extraction. And what you'll do is you'll take underneath the spill that you have, especially if the compounds fit into, they're very easily volatilized. They're a VOC, they've got low boiling points, they're high vapor pressure. what they can do is they can dig underneath them, and then they put gas in there, and then as the gas is going through it, it volatilizes it, and then they have like a vacuum on the surface, and then they can vacuum up all the gases and then get rid of it. And so it's a remediation strategy by understanding these basic physical properties of the organic compound. So understanding these basic what causes it, and so that when you look at a molecule, you can make predictions. If I gave you 2 molecules on a homework assignment, you should be able to make, or an assignment, you guys should be able to make a prediction as to how attracted they are, what the boiling points are, the vapor pressure, based upon the size, the surface area, the forces, the bipole-pipole moment, does it form hydrogen bonding. Okay, so back again. The next thing we're going to talk about is solubility. So over here, solubility. So this is the basic adage of like dissolves like. This is very important. So a nonpolar molecule will dissolve a nonpolar molecule. A polar molecule will dissolve a polar molecule. So the closer they are to liking each other, the more their solubility increases. So why do water and alcohol mix together? Because they're like compounds. They're both polar compounds, so they will, like, it dissolves into there. So water is very polar, quite polar. It's a very polar molecule. So organic molecules that are polar will dissolve very easily inside of water. An example of this, and I've already kind of talked about this a little bit, is with methyl tert-butyl ether. And that compound here, this is also referred to as MTBE. And that molecule looks like this. So it has a lot of polarness to it, so it's a very polar molecule, and since it's polar, it can be dissolved into water and it can form H bonds into there. So something is also referred to as miscible. You're going to hear me talk about something being miscible or immiscible. So this is where a liquid dissolves another compound. So, and if it's immiscible, they don't. It's not dissolved into each other. So ethanol is very miscible in water because of H bonding. So because water can do it, so it's miscible completely because it can dissolve inside of there. So if we increase the number of functional groups onto a compound, it's more water soluble. So that just gives you an idea of that. So this is why, one of the things that you will find out about is, like, if you have a lot of hot food and stuff, if you drink water, it's not going to help you because you're not doing like dissolves like. So the compounds within inside of, like, hot peppers and jalapenos are organic molecules, okay, but they're not polar. They don't have a lot of polar aspects to them. They can't form H bonds. So what happens is when you drink water, you really are not dissolving that compound. You really need something that's like it to dissolve it. So this is why having milk or sour cream or even beer, things like that, that'll help that's got organics into it, or, like, non-polar molecules to help wash it away. So, like, yesterday I made dinner with Mom and I made pink sauce, which is just sriracha mixed with sour cream, and you mix those two together. And normally sriracha is way too hot for my mom, but mixed with the sour cream, she's like, "Oh, this is amazing." And I'm like, "Yeah, this is called pink sauce, and it's really good." So it just gives you an example, so that if you're ever going out and you're having really hot food and stuff like that, it's burning your mouth, don't drink water, get some fat into there or something like that, and that will help to dissolve it.